Welcome to TVE Happy Math Hour, our weekly interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Aberti Sassi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now, at this time, please mute your mics for the best sound experience, otherwise the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Ms. Patricia will be sending individual messages to everyone to gather your student ID numbers to sign you in. Without further ado, I'll pass it on to our presenter so that we may begin.
Good morning, everyone, and happy that you are joining us today for this Friday Happy Math Hour. I hope your semester's going well. We're past the halfway mark, so you can do it, okay? So for today's session, we will be doing exponential and logarithmic functions. And as stated, anybody who's here for the Math 1324, please click on the link that's on your chat. We'll give a few seconds for those students to go ahead and transfer, and we'll get started shortly. Okay. So again, I want to remind you that if you have any questions, please raise your hand or just go ahead and unmute your mics and stop me, and I'll answer any questions or go over any things you may have. Okay, so let's go ahead and get started. So let's first start by defining what an exponential function is. So the definition of an exponential function is a function that has a base. And in this example, we denote the base as a. Again, the x represents the exponent. So a has to be greater than 0, and a cannot be 1. Okay, so and x is any real number. All right, so to review domain and range, the domain of all exponential functions is a set of all real numbers, while the range is a set of all positive real numbers. Okay, so keep these things in mind. All right, so let's look at some basic properties. So if I wanted to graph this exponential equation y equals a to the x, and again, a is going to be a value greater than 1, all graphs will pass through this y-intercept at 1, okay, at the point 0, 1. All graphs are continuous curves. And just to remind everyone, continuous means that it's a smooth line. There's no breaks, sharp turns, or curves. And it has no holes. And again, no jumps. The x-axis is a horizontal asymptote. Yeah, and a horizontal asymptote is this imaginary horizontal line that the graph does not cross or touch. And if a is greater than 1, then a is increasing as x is increasing. If a is a fraction, meaning if it's a value between 0 and 1, then the exponential equation or function is decreasing as x is increasing. Right? So see, these are some basic properties. So as a diagram to just explain what we just covered, okay? Again, our exponential function is a smooth line. It goes forever to the left, goes forever to the right. It's going to cross the y-axis at 0, 1. And again, the domain in interval notation is from -infinity to +infinity, all real numbers. And the range is in interval notation from 0 to infinity, all positive numbers. Again, the graph is increasing if a is a positive value, and the x-axis is a horizontal asymptote. Again, we don't see it here, but we represent it as a dashed line. The x-axis would be our horizontal asymptote. Again, and this graph and function is continuous. So if I wanted to graph an exponential function, the best way is just to go ahead and create a table, plot the points, and do the smooth curve. So when I give these values for x, -4, -3, -2, 1, 0, 1, 2, just a quick example, if I plug in -4, we have 2 to the -4th power, but we need to use some of our fundamental properties of exponents. To evaluate this, we take the reciprocal of the fraction and then change the sign of the exponent, which will give us 1 over 2 to the 4th. So 2 to the 4 is 2 times 2 times 2 times 2, which gives me 16. So 1 over 16 is the first y value. And again, if I would plug in 0, um, 2 to the 0 power, anything to the 0 power is always 1. Keep this in mind, okay? Anything to the 0 power or 0 as an exponent, the answer will always be 1. So when I plot all these points, -4 and 116, -3 and 1/8, um, I plot them and connect them with a smooth curve, and this is what it looks like. All right, so let's look at another example of this graph. So here we have 2 to the -x. Again, I'm going to use a fundamental property to eliminate the negative exponent. I take the reciprocal of this, or if you don't see it, what I can do is create this as a fraction, 2 over 1, take the reciprocal, which is 1 over 2, and by me doing this, the exponent becomes a positive. All right, so if I'm reviewing this exponential equation, the domain, again, is negative infinity to positive infinity. Please keep in mind a key, giving you a key point for your exams coming up. Um, the domains for exponential equations will always be this, from negative infinity to positive infinity. These will never change. What will change is the range, and we'll see that shortly. But for this example, again, the range still here is all positive values from 0 to positive infinity. Again, it still has my y-intercept, 0, 1. Um, Now, because as stated before, since my base is a fraction, okay, it's going to be decreasing, okay? So, so this is two ways that you'll see that it's a fraction is decreasing. If my base is a fraction or a value between 0 and 1, or if my exponent is negative. If my exponent is negative, we're going to have a decreasing function. Again, the x-axis is still my horizontal axis. And again, this is the continuous graph. All right. All right, so let's look at some more properties that I just mentioned to you to review so you can have. These are some fundamental basic exponential properties, and or we call these laws, right? Um, so when we have two exponents that are being multiplied to each other that have the same base, you will add the exponents. So for instance, if I had a times a, this would give me a, they would have an exponent of 1, so 1 plus 1 would be 2, a squared, right? So inversely or opposite to that, if I have two exponent equations that are being divided that have the same base, I will subtract the exponents, okay? So again, if I had a squared divided by a, I would subtract a squared minus 1, which would give me 1, a to the 1 power, right, as examples. All right, so the first one was called the product rule or product law. The second one is the quotient rule or quotient law. And then we come to the power rule or the power law, that we have an exponent and we take it to the another exponent, we are going to multiply the exponents, okay? And we can do it also the distribution property for exponents. If I have an exponent and I have a product going inside, I have to distribute that exponent and multiply it to all of my terms inside. So ab to the x power is the same thing as a to the x times b to the x, okay? And also if I was dividing values inside the exponent, okay, I still have to distribute the same way. The exponent has to be applied to all of the terms inside that parentheses. So this would be equivalent as a to the x divided by b to the x, okay? So x, again, cannot be equal to 0. Um, and we have what's called a one-to-one property, okay? And this is going to be very useful to, to solve exponential equations. And the one-to-one property states this, that if I have two exponents equal to each other, the only way that these two exponents can be equal to each other is if the bases are the same and the exponents are the same. And this would make sense, right? If I have different bases or different exponents, of course, they're going to give me different numbers. But this property is called the one-to-one property, that for it to be one-to-one, we have to have the same base and the same exponents to both sides of the equation, okay? All right. So let's go ahead and look at an example on solving exponential equations. So let's solve this given equation. 10 to the exponent 2 minus 4x is equal to 10 to the 6x minus 1. So the question is there, right? Can we use the one-to-one property? And the answer would be yes, right? I have two equations that have the same base. So for these two equations to be equal to each other, then the exponents have to be equal to each other. So that's what I'm going to do. To solve this, I'm going to set the exponents equal to each other and then just do a simple algebra to solve for x. So I always like to move the variables to the left and all the numbers to the right. So that's just what I'm going to do. Okay, I'm going to subtract the minus 6x to be on the left, and I'm going to subtract the 2 to be on the right on both sides. Okay, so when I do the math, I have minus 10x is equal to minus 3. So to solve for x, I'm going to divide both sides by a negative 10. And when I do that, a negative divided by a negative is a positive, and x is equal to 3 over 10. I can't simplify that anymore, and I'll leave that there. So I've done it. I use my one-to-one property to solve for x on this equation. All right. Again, if you have any questions, if I'm going too fast, please let me know. All right, let's look at another example. Solve the given equation for x. 4 to the x plus 1 is equal to 64. And I will throw this question to you again. Can we use the one-to-one property? And I hope that you can see that the answer would be yes. Even though it doesn't look like it, we can do a little bit of our rules or properties to make this look like a one-to-one property problem. So what I can do is my first step is to rewrite the equation so that both sides have the same base. And I say to myself, can I write 64 as a base of 4? And hopefully you can see that the answer would be yes, 4 to the third power. Now, one way to do this, and let me help you a little bit. If you can't see this right away, what I usually tell my students is to create a factor tree of the base that you want. So for instance, I want to have 64 and I want to see if I can make it into a base of 4. So what I'm going to do is I'm going to do a factor tree that has numbers divisible by 4. And I go, can 4 be divided into 64? Yes, 4 will go into 6 one time, remainder 2. 4 will go into 4 6 times. So 4 times 16 is 64, and then I will do it again. Then can I divide 16 by 4? So the answer would be yes. 4 will go into 16 4 times. So I have the building blocks of 64 could be 4 times 4 times 4, hence 4 to the third power. Okay, so now we can see that this is a one-to-one property problem. So for this equations to be equal to each other, since they have the same base, the exponents have to be um, equal to each other. So then I will set the exponents equal to each other. X plus 1 is equal to 3. Solve for x by subtracting 1 on both sides. So x is going to be equal to 2. Yes, so questions? All right, let's go ahead and look at this example. Uh-oh. Um, and believe it or not, again, I think I clicked it too quickly, but no, oops, messed up on the animation. But if I had this equation, 5x minus 3 is equal to 1 over 125, I can use my one-to-one property. And what I'm going to do is I'm going to rewrite it so that I can have both sides have the same base. So first of all, what I would do first is the 125. I can do a factor tree to see if I can make it into a base of 5, and I would see that I can. 5 to the third power would give me 125, but it would be as a fraction, 1 over 5 cubed. So I'm going to use one of my laws to get rid of that or to move the base up. And I take the reciprocal and I change the sign. So this is going to give me 5 to the negative 3. So now I can see that it's a straightforward one-to-one property. For this equation to be equal, the exponents also have to be equal. So I would set my exponents equal to each other. X minus 3 is equal to negative 3. Add 3 on both sides to solve for x, and I get x is equal to 0. And again, when you're doing these problems either on your homework or on your test, it's also good to check to see that your answer is correct. So if I would plug here 0 for my problem, 5 to the 0 minus 3, 0 minus 3 is a negative 3. To evaluate that, I would take the reciprocal and change the sign of the exponent. It would give me 5 cubed, and 5 cubed is 125, and they would be equal 1 over 125. Okay, so always it's a good rule to check our work. All right, now let's look at what we call base e exponential functions, and mostly e we use those in business. Um, but e is just a number. It's an irrational number. Some of you guys may not be familiar with e, but some of you guys are familiar with the symbol pi, right? Pi represents an irrational number, 3.14, that it goes on forever, never repeats. Well, same thing with e. E is this irrational number that is roughly 2.7182, blah, blah, blah. It keeps on going forever, okay? So we call this the natural base, okay? And we write this as the function f of x is equal to e to the x. As an exponent, we call it the natural exponential, okay? Now, let's look at some properties of this. Believe it or not, this looks a lot like the um, parent function that I gave you in the beginning. 2 to the x is the um, same graph, okay? Um, it has a horizontal asymptote at x equals 0. It's going to cross the y-axis at 0, 1. Again, this is a continuous graph that goes forever to the left and forever to the right. All right? So let's solve some of the um, natural exponents using some of our properties. So again, we can see that we have two exponential equations that have the same base. They both have a base of e. So for these two equations to be equal to each other, our exponents also have to be equal to each other. So then I'm going to set the exponents equal to each other. I'll have x squared minus 3 is equal to 2x, and then I'm going to solve for x. But I noticed something. I have a square, so it looks like I'm going to be solving for a quadratic. So what I'm going to do is I'm going to move everything to one side. Okay. So what I'll do is I'm going to move the 2x to the other side for I can have a quadratic in standard form. Okay. So when I do that, I have this: x squared minus 2x minus 3 is equal to 0. Now that I have it in a quadratic form, again, you've all seen that there's several ways that we can solve for x. We can use our quadratic formula, or we can factor this problem. So for me, I always like to factor. That's the easiest or first route to go always. And again, as my colleague Ms. Chuka would always say, try to factor it. And if you can't factor it within the first couple of, let's say first minute, then it may not be factorable, and use the quadratic formula. Again, your quadratic formula will never let you down. It always will help you get a solution. Okay, so if I factor this x squared minus 2x minus 3, I came up with this x minus 3x plus 1. And the way I do it is I say to myself, what are the two numbers that when I multiply them together give me negative 3, and when I add those same two numbers give me a negative 2. So, and those numbers would be a negative 3 and a positive 1. Negative 3 times a positive 1 is a negative 3. That gives me the C value. And a negative 3 plus 1 is a negative 2. Hence, this factors out in this format: x minus 3 times x plus 1. And I use my zero property to solve for x. For this to be equal to each other, again, I will solve for x minus 3 or x plus 1. Here, hopefully we can see that if I plug in 3 for x, 3 minus 3 will give me 0. So that is a solution. And negative 1. Negative 1 plus 1 will give me 0. But you also have to be careful with our exponential functions. We always want to test and check that both of the solutions will give us um, an answer or a true statement. Okay, so um, let's switch over to logarithmic functions. Believe it or not, logarithmic functions is the inverse or the opposite of an exponential function. So, and this helps to be able to to the to graph and determine between the two. But let's look at some of the first, the definition, and then some properties. Okay, so a logarithmic function also will have a base b. Okay, we use the word logarithmic. We shorten it and just call it a log. Okay, and our x in this case is going to be our input. Again, our y will be our output. If I were to convert this log into exponents, okay, this is a very key feature to think about because some of you may be scared of logs, because again, your calculator, there's some calculators that only evaluate logs of base 10. Why 10? Because 10 is the counting numbers that we use. The counting numbers that we use every day are from 0 to 9, 10 digits. So your calculator only does logs of base 10, but we will be evaluating logs of different bases. So if your calculator cannot evaluate logs of different bases, you can always evaluate an exponential equation. And we can do this by transforming it to its inverse. So the way to do this is this format. The base of the log will also be the same base of the exponent. The input of the log becomes the output of the exponent, and the output of the log will become the input of the exponent. They're inverses of each other. Everything's the opposite. Okay, so the log of a base b function um, is an exponential function raised to the output, right? So the domain of the logarithmic function is a set of all positive real numbers, right? And that was, and then the range of the logarithmic function is a set of all real numbers. So let's look at this a little bit more detail back to back, okay? So again, what I drew here are my parent exponential function and my parent log function. So my parent exponential function, again, has a horizontal asymptote at x equals 0. It's continuous and its y-intercept is at 1. Okay. Inversely, the log has opposite of a horizontal asymptote, it has a vertical asymptote. So my log function has a vertical asymptote at y equals 0. Okay. Um, I'm sorry, excuse me, x equals 0, not y, x equals 0, and it has a x-intercept at 0, okay? It has an x-intercept at 1, okay? Again, it's a smooth curve, okay? The Remember the domain for the exponential function was from in interval notation from negative infinity to positive infinity. Now that's the range for my log function. My range for my log function is from negative infinity to positive infinity. My range for my exponential function was from 0 to positive infinity. Now that is my domain for my log function. My domain for my log function is from 0 to positive infinity. They're opposites of each other. They're inverses. Okay, and if I draw them, we have this axis of symmetry, which is y equals x. It crosses it cuts our quadrant in half. Okay, all right. So let's look at some common log and natural logs, the difference. Again, the common log is a base 10. And when it's base 10, since our calculator can do this, we usually don't write the base. So if you see on your homework a log and they don't write the base, we're assuming that is a base 10. Okay? Um, so its counterpart is their natural log. Just like we had a natural exponent, we have a natural log. And the way we represent the natural log is by this, ln. We say ln is our natural log of x, which is equal to the log of base e to the x. Okay, again, e is this symbol that is represented by this 2.71 estimation. Okay, all right, so let's go ahead and practice these conversions that I mentioned that our definition gave us or helped us. The, you might have a homework problem that says write the logarithmic equation in exponential form or vice versa. So problem number one, they're giving me a log and it has a base 4, its input is 16, and its output is x. So I can convert this into an exponential equation because my calculator might not be able to solve this, but look, if I convert this to a log, to an exponent, um, the base of the log will become the base of the exponent, and the input of the log is going to become the output of the exponent, and the output of the log is the input, right? So 4 to the x is equal to 16. So if they took it a step further and asked us to solve for x, it would be very easy for us to solve for x, right? I know that 4 squared is 16. And I didn't even have to use a calculator to solve for x. Now in the logs, it would be a little bit different, right? It's like, I wouldn't know what x is. But as an exponent, it's really easy for me to see what the answer is. Okay? So this will come in very useful. How about this one? Um, Now they're giving us an exponential equation, and they want me to convert it into to a log expression. So same process. I have a base 5 for the exponent, so that means that my log will have a base 5 as well. The input of the exponent, which is 3, becomes the output of the log, which is 3. The output of the exponent, the 125, becomes the input of the log, which is 125. All right. So again, it would be hard for us to evaluate log of base 5 of 125 equals to 3, or if they just ask us to evaluate log of base 5 of 125. But if we had the exponent version, 5 cubed, oh, I can do that. 5 cubed is 5 times 5 times 5, which will give me the 125, right? All right. How about this one? No numbers. Log of base b of 27 equals 3. Again, my base didn't give me a value for the base, but I can convert this to an exponential. So the exponential expression would be base b. The input of the log is 27, so that becomes the output of my exponent. The output of the log becomes the input of my exponent. So this is b cubed is equal to 27. And hopefully we can see that, oh, I know what b now is. I know that if b would be 3, 3 times 3 cubed would give me 27. 3 times 3 is 9, 9 times 3 is 27. So this is very useful to use when solving equations if we know these fundamental properties. All right, how about this last one? The square root of 81 is equal to 90. And I like to give this example because um, we might have forgotten that we can rewrite the square root as an exponent. The square root can be written as a 1/2 as an exponent. So if I were to do this, okay, um, um, first, before I convert it to a log, I would represent the square root of 81 as 81 to the 1/2 power. 1/2 power is the representation of the square root. So 81 to the 1/2 power is equal to 9. So now it's easy to see that I can convert this to a log. My base is 81, so hence my log is going to have a base of 81. The output of the log becomes, I'm sorry, excuse me, the output of the exponent becomes the input of the log, and the input of the exponent is going to become the output of the log. Okay, so the answer is log of base 81, input 9 equals 1/2. Okay, so hopefully this helps. Again, if any questions, please raise your hand, put it on the chat. All right, so let's look at some properties again for our logs. Okay, and we like to use just the word logs. So as math people, you don't like to use big words, logarithmic. I like to use log, right? So um, these are some basic properties. We have our identity property that if I have a log of whatever base, but my input is 1, my answer will be 0. Okay, just like it's like the opposite of my exponent. Remember, if I put in a 0 for an exponent of any base, the answer is always going to be 1, right? Or how about this one? This was our identity property. If I have a log of base a and my input is a, the answer will be 1. Okay, so inversely, as the exponent, if I have a to the 1, that's just a, it's just the base itself. Okay. Now we also have a power rule that it says that if we have a log of base a to an input of a to the exponent, we're just going to multiply that exponent to the log, okay? And we can also use an inverse property. We can convert that to an exponent of a to the log of x base a of x, which is again give me the same value x. Okay, and again the one-to-one property. Logs also have a one-to-one property. For two logs to be equal to each other, they have to have the same base and they have to have the same input value. Okay, so hopefully it's straightforward. So let's go ahead and use some properties to solve this equation. Again, I can solve anything without using a calculator. So, and I'll do this by um, converting it to exponential. So I have a log of base 3 that has an input of 1 over 27. So what I'll do is, let me see, I can solve this by using my one-to-one property, okay? So let's go ahead and do this. Let's convert it to an exponential form. So my base is 3, so that's going to be the base of my exponent. My input of the log becomes the output of my exponent, and what I'm trying to solve for is the output, right? The exponent part. So I gotta say to myself, what 3 to the unknown power will give me 1 over 27? Well, I know that if I have 3 cubed, that gives me 27. 3 times 3 is 9, 9 times 3 is 27, but I need that as a fraction. So it would be like this, 1 over 127. And I know that when I have a value on the bottom, to move it to the top becomes a negative, right? So this is 3 to the negative 3. So this would be my answer. Um, Log of base 3 of 1 over 27 would be 3 to the negative third power. Okay? And again, applying my basic rules, and at the end, finalizing with my one-to-one property. All right. Um, so let's go ahead and review some of the properties that we use. Again, to solve for this problem, okay, we see that we first had to convert the 27 into an exponent, and then I rewrote it as a um, exponent to with the exponent on top, and then I converted it to an exponent form. So which of these properties resembles the final result? Okay, so we see I could also apply my inverse property, right? So if I have a log of base 3 and my input is 3, the answer is just going to be the exponent, the negative 3, right? So it's another way to be able to solve for these problems. Okay? All right, let's go ahead and solve for this one. Use properties to solve. Log of base pi, and my input is pi to the ninth. Again, instead of doing some conversions, we can use what I just explained to you right now, right? I can use my inverse property or just some of my properties that when I have a log of a base and it has the same input value, it's gonna give me only the exponent, right? So the answer, hopefully you can see that it's the same property, the inverse property, and my answer is just gonna be 5, right? So how about this one? Something with a decimal value, log of 7.5 input 1. What is going to be my answer? Or what property would I use? Hope you all see that we would use the second property, right? That or excuse me, the first property that any input that I plug in for 1 is going to give me a 0, right? So my answer would be 0. Okay. All right, how about this one? Log of 90, input 90. Hopefully this one is easy to see, right? Which one is this one? This is my identity property, right? That property number 2, that when I have the log of some base and it's the same thing that I'm inputting in, the answer will always be 1, right? It's this one. Log of A with an input A, the value will be 1. Okay. All right, how about this one? Log excuse me, base 3 of log of base 3 to the 8th power. Okay, which property does this example resemble? This is my inverse property, right? Um, that I have, if I have a exponent of a base and I am taking that to an exponent with a log of the same base, the input is just going to be my answer. The answer is just going to be 8, right? So, all right. Let's solve some a little bit more equations where we can't really use our one-to-one property, or maybe we can, right? So the problem says use definitions of logarithms so to solve the given problem. So we have log of base b of 1000 equals to 3. So how can we do this? So what I would do is first convert it into an exponential problem. The base of my exponent would be b. The output of the log is the input of my exponent, and the input of the log is the output of my exponent. Then I can say to myself, oh, what value for base will give me 1000? So hopefully we can see that that would be 10, right? 10 cubed. 10 times 10 is 100. 100 times 10 is the 1000. So the answer would be 3. Yes? All right, so my base is 10, and my b would be 3, right? And that's what I'm solving for. Sorry, I'm solving for the base. Excuse me, my base would be 10. My exponent is 3, and my base is 10. All right, so let's look at and review some properties of logs that are going to be handy for some homework problems that I'll review right now. Okay, so I already went through the first four, some of the fundamental properties, but let's look at these additional ones. Okay, and they have kind of the same properties of exponents. So remember when we saw that we're multiplying two exponents that have the same base, we added the exponents. Well, the logs have a similar feature. When I have a log of a base and I have two values that are being multiplied within that log, I can expand them to two logs of the same base. I would add the values, the log of base b of m plus the log of base b of n. If I have a product, I will add logs. Inversely, if I have a log that has a base and the inputs are being divided with each other, I can expand it or separate them to two logs by subtracting the logs. The log of base b of m minus the log of base b of n. Again, this represents like my exponents. If I have exponents that are being divided and they have the same base, I would subtract the exponents, right? We also have a power rule or our power law that if I have a log of base b and input m and I'm taking the m to another exponent, I will multiply that exponent to the log. This would give me p times log of base b of m. Okay, and then we also have again the one-to-one property for logs. That if I have two logs that are equal to each other, the statement says if and only if, right? M is equal to n. If we have the same base, then the exponents will be the same for these two logs to be equal to each other. Okay, so again, number 8 represents my one-to-one property. Right, so let's for this. Um, um, this example, solve for x. Log of base 5 of x plus 1 is equal to log of base 5 of 9. So we see that we can apply our one-to-one property because we have the same log on both sides. We have a log of base 5 on the left, a log of base 5 on the right. So for these two logs to be equal to each other, then that means that inputs have to be equal to each other. So again, this is a one-to-one property. I get ahead of myself. So it's the one-to-one property. And I'm going to set the inputs equal to each other. The x plus 1 is equal to 9. So solving for x, I'm going to subtract 1 on both sides. So x is going to be equal to 8. So again, our one-to-one property, I love it, will always come to my rescue to solve a log or exponential equations. Okay. All right. So um, I'm gonna go ahead and go through some of these a little bit quicker, right? Because I think we've got them, right? If I have a log of base 5 of a plus 1 is equal to a log of base 5 of 9. If I plug in the value that I just solved, I'm going to see that 8 plus 1 is 9. Yes? All right. So again, can we use the one-to-one property for this one? Hopefully, yes. The answer is yes. These two both are the log of base 10. Since they didn't write a base on there, we know that, and we can assume that it's a base 10. So yes. So for these two logs to be equal to each other, the inputs have to be equal to each other. This 17 is equal to x squared plus 8. Uh-oh, I have a square, so I know that I'm going to have a quadratic. So I'm going to move everything to one side. Again, I would try to factor it first, and if I can't, I use my quadratic equation. You can see that this is a perfect square, and I can use my square root property, or I also know that by factoring gave me a difference of squares, but since I have it in this format, I'm just going to use my square root property to solve. Add 9 on both sides, take the square root of both sides, and this is going to give me x is equal to plus or minus 3. Okay, so we always want to check our solution, especially for logs. We cannot put negative input values to logs. We would get an error on our calculator. All right, so let's check. Will these two values satisfy our condition? So if we put 3, um, for a positive 3, we are going to get a 17. So yes, this gives us a true statement. And if I put negative 3, we also get a log of 17 on both sides. So yes, we do have two solutions for this example, x equals negative 3 and x equals 3. So again, I want to stress this. Always check your answer, especially for logs. We cannot have an input for a log that is negative. Okay, keep that in mind. All right, how about this one? Can I use my properties? Well, this is a natural log, but hopefully it's easy to see since natural logs are natural logs. We can use our one-to-one property. They're both the same logs for them. So for us to solve for these two logs, our inputs have to be equal to each other. So again, I will set my inputs equal to each other. The x squared minus 3x is equal to 18. Oh, I have another quadratic. I'm going to move everything to one side. I have x squared minus 3x minus 18. Can I factor this guy? Yes, this factors by x minus 6 times x plus 3. So I'll have two solutions. X minus 6 is equal to 0 or x plus 3 equals to 0. So my solutions are going to be x equals 6 and x equals negative 3. But again, do not forget to check. Let's go ahead and verify that it'll give us true statements. Okay. Oh, and I didn't check, but I want you to go ahead and you guys do that. Make sure you double check. Okay. What about this one? Um, log of base 4 of x plus 6 plus log of base 4 of x minus 6 is equal to 3. Hmm. What property can I use? Right. So I hope you can see. Oops. Um, I didn't do it, but I'll do it really quickly. Okay. Um, if you see here, it represents this. I have two logs that are being added to each other that have the same base, 4 and 4. So what I can do is I can condense these two logs to one log. We can have me log of base 4 of x plus 6 times x minus 6, okay, equals to 3. Okay, and then now that I have it in this format, I can do that multiplication. That's going to give me x squared minus 36, and then I can use my exponential property to solve. Okay, so I'll leave that up to you guys. So let's solve for this one. Log of base 5 of 125 is equal to x. Um, the way I would do it is I would convert it to an exponential equation. So let's change it. The the base of this log um, becomes the base of my exponent, okay, which is 5. The input of the log becomes the output of my exponent, and the x is the input of my exponent, right? So 5 to the x is equal to 125. Hopefully, we can see that I can convert the 125 to 5 cubes, so I can automatically just see that it's a 1 to 1. So for these two equations to be equal to each other, x must be equal to 3, right? So, and again, 3, 5 to the third power is going to give me 125. All right. Um, how about this one? Log of base 2 of 25 is equal to x. Okay. Again, I would do very similar. Let's change it to exponential form. My base is 2 of my log, so it's the base of my exponent. Uh-oh, but we come to a problem. Um, I don't think there's any value that I can convert, that I can give to x that would give me 25 on this one. Uh-oh. So on this one, um, there's no way to rewrite 25 as a base 2, so we will need to use a calculator for this one. So a calculator will be handy for some other problems, okay? So the way you can do it, again, these are some picture representations on how you can do it. Be careful. Um, you have to have a feature on your calculator that lets you change the log, the base, excuse me. If I'm evaluating this one, the first one on the Texas Instrument, um, this is going to assume that it's a base 10 is going to give me the wrong answer, okay? It's because it's going to evaluate the log of base 10 of input 5. But what I want to do is I want to have the log of base 5 of an input, okay? So this is an example on how you would plug it into your calculator if you're allowed to change the base, okay? But let's say that your calculator does not have this feature. We have something that's called the change of base formula that will allow us to evaluate any log that is not of base 10 using a calculator. And what we would do is we would use this middle one, the base 10 example. Let me give you an example on how to use this change of base formula. So let's say that I want to evaluate this log of base 3 input 11. And again, my calculator doesn't have a way to um, change the base. So what I would do is I would use my change of base formula and the change of base formula says this, that I take my input and I'm going to evaluate this as a log of base 10. And I'm going to take the base and evaluate that as a log of base 10. So it's a quotient, right? So the log of 11 divided by the log of the base will give me the answer that I'm looking for. Okay, so this is going to give me, and if they want me to round to 3 decimal places, the answer will be 2.183. That 2 gets rounded up because that number to the right was greater than 5, right? So how about B? Um, B is, again, I wouldn't be able to calculate that by hand. So I'm going to use my handy calculator. I'm going to take the log of zero point 0.5, the input, divided by the log of the base, which is pi. And again, the calculator will represent pi as that 3.14 blah, blah, blah number, right? And when I do the division and rounding to the nearest or to the 3 decimal places, is negative 0.606, right? To the thousandth place, right? If we were to say the word. All right. Um, so again, these are some of your properties just reviewed. So let's go ahead and use this example. Use properties of logs to write the logarithmic in terms of log of base 5 of 2 and log of base 5 of 3. So they want me to span this or separate this to 2 logs. And what I see is, can I represent 6 into a product so I can expand it? And the answer would be yes. 6 can be rewritten as 3 times 2 as a product rule, right? So if I have this log of base 5 of 2 times 3, I can use my product rule that and expand this into 2 logs. I can create it into what they're telling me. Log of base 2, I'm sorry, log of base 5 input 2 plus the log of base 5 of 3 is the same thing as log of base 5 of 2 times 3, which is the original problem, log of base 5 of 6, okay? So this is a very common question that we get asked a lot on their homework, and we're just using our basic rules to manipulate the 6 into a product, okay? All right, how about this one? Find the exact value of the logarithmic expression without using a calculator. And a lot of students, you'll use a calculator on the homework and the computer is going to mark it wrong. Okay, so please be careful. And we can solve for this. This is an easy problem if we know our properties. So the first thing that I would do is I would rewrite the cube as a power. So the cube root of 4 can be rewritten as the log of base 4 of 4 to the 1/3 power. Then I'm going to use my power rule that says that I can move that exponent and multiply it to the log. So it's going to give me 1/3 log of base 4 of input 4. Oh, then I have my identity, right? That a log of base 4 to an input 4, that's just 1. So um, 1 times 1/3, the answer is going to be 1/3. Easy. Did not have to use a calculator. And if I know my properties, I can solve these and that would be the exact value. Please keep in mind when they say exact value is the fraction. They don't want to see decimals are estimations. Okay. So please be careful with these when asked not to use a calculator. So how about these? Find the exact value of the logarithmic expressions without using a calculator. Let's do A. Um, and I'll do these two fairly quickly. Again, I think we got the gist, so I can get through most of our information. So we have natural log of the fourth root of e cubed. I'm gonna rewrite this as an exponent. Okay, um, so I have the natural log of the fourth root of e cubed. If I convert that to an exponent form, this is natural log of e cubed to the 1/4 power. You see that I have multiple power rules. So I first use the power rule um, to to multiply my power 1/4 to the third, which is going to give me natural log of e to the 3/4 power. Then against the power rule that I have 3/4 multiplied to the log. So we have 3/4 times natural log of e. Again, natural log of e is the inverse property, so that's going to give me just 1. So 3/4 times 1 will give me just 3/4. Okay. Similarly, for the second one, I can apply my power rule and um, multiply the exponents to the logs. Okay. Um, then I can evaluate the natural log of e. I know that's just 1. So that would be 4 times 1 plus 8 times 1, and 4 plus 8 is 12. Okay, so if you see that if we know our properties, they come really, really handy to solve these equations without having to use a calculator. Okay, so this is what I was mentioning to you right now. You're going to have some homework problems where they're going to ask us to expand to multiple logs. So let's look at this example, natural log of z times z minus 1 to the fourth power. And it says, um, expand expression as some differences or as constant multiples of logs. So let's get to it. The first thing that I can see is that I can apply my product rule. I have a log and I have two things that are being multiplied to each other within that log. So I can separate it like this. Natural log of z plus and I'm missing the, sorry, this is supposed to say natural log here as well. Natural log of z minus 1 to the fourth power. Okay, I'm going to apply my power rule. Now it's fixed. 4, a natural log of z plus 4 times the natural log of z minus 1. Okay, and I'm done. Okay, this would, oops, that would have been my answer. So I think I have time to slow down and this will be my last example. Okay, um, this is a problem that you'll see maybe on a homework or a test. Okay, um, it says use properties of logs to expand the expression of some difference and or constant multiples of logs. So I have log of base 5 of the input, the square root of x squared minus 9 divided by 4. Okay, um, and let's do it. So first, I'm going to apply my quotient rule that it says that when I have a log of the same base that the inputs are being divided, I can do two logs. Log of base 5 of the numerator, square root of x squared minus 9, minus the log of base 5 of denominator, 4. Okay, now I have an exponent property because I can convert the square root as an exponent. So we have log of base 5 of x squared minus 9 to the 1/2 minus log of base 5 of 4. Again, I'm going to apply my power rule, multiply that 1/2 to my log. So it's going to give me 1/2 log of base 5 of x squared minus 9 minus log of base 5 of. And what most of my students have done, or especially my online students, they leave the answer like this. Okay, but we can still do some more to this. This x squared minus 9 is a difference of squares. It can be it's factorable, okay? So x squared minus 9 can be rewritten as x minus 3 times x plus 3. Oh, so I have a log that the input have two items that are being multiplied to each other. So that I'm going to use now my product rule or product law, right? So this the final answer would be 1/2. I got to keep the 1/2, okay? That's being multiplied to log. So I have 1/2 log of base 5 of x minus 3 plus 1/2 log of base 5 of x plus 3 minus log of base 5 of 4. This one can't be simplified any further. Okay. All right. Any questions? Again, let's see. I think I have room for one more. I still have 5 more minutes. Let's see. Let's do this one. Log of base 8 of x cubed over y cubed over z to the fourth. Again, apply my quotient rule, which is going to give me log of base 8 of x cubed minus log of base 8 of y cubed z to the fourth. So the first one I can apply the the power rule, and then and for the second half it's a product rule, right? So I haven't touched the first one yet because let's do it one step at a time. The right side is a product rule. That means that I have two things that are being multiplied to each other. Then I would add log of base 8 of y cubed plus log of base 8 of z to the fourth. Now, when you have a subtraction on the right, and I'm expanding, we gotta use parentheses because we have to follow the rules of order of operations. Okay, so when you're subtracting and you're needing to do more stuff on the right side, please use parentheses. Okay, so now I'm going to apply my or I can distribute my negative rule if I want to get rid of the parentheses. Okay, so it's going to give me log of base 8 of x cubed minus log of 8 of y cubed minus log of 8z to the fourth. Then the last thing is applying again the power rule, just to do them all at once. So applying the power rule is going to give me 3 log of 8x minus 3 log of 8y minus 4 log of 8 base 8z. Okay. Um, yeah, this B, I'm gonna just show it to you fairly quickly. We've done this several times. We convert the 10th root into an exponent, becomes power rule, and then we have a product rule inside, and then we have a power rule for one of them. Okay, so and we can distribute again. We could have distributed the 1/10 if we want to get rid of our parentheses. And I believe the computer in your homework, if you leave the 1/10 outside and don't distribute, it would still count it right. Okay, you don't have to distribute, but if you want to, that's fine. All right. Um, how about the opposite, condensing? I just want to do this last one, have time to condense, going the opposite way. So I first, please keep in mind, if I want to condense or use my properties, they have to be the same base. In order for me to apply all these properties that I've been doing, they've had the same base. So on this one, the log of base 6 of 3x minus the 9 times the log of base 6 of x. I can start working with these two because they do have the same base, okay? So the first thing that I want to do is apply a power rule to the right side. I have um, a 9 being multiplied to that log, so that becomes an exponent, log of 6x to the 9. Now that I don't have any more power rules, okay, now I can condense. I have two logs that have the same base and are being subtracted from each other. This is a quotient, okay? So we have log of base 6 of 3 to the x over x to the 9. Again, guys, thank you for joining me today. This session will be recorded and we also upload the slides. So all the slides that I didn't get to, you will have them available for you. Again, thank you for joining me.
Thank you, Mr. Carizales, for your presentation. Again, we do want to remind you all about our previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and remember to send your student ID number to us before you log out. If you would like to download a copy of the presentation, you can go to the top right corner and click on the box with the little arrow going down while the presentation is on the screen. That's going to allow you to download the presentations. Before you all leave, I want to share the TVE sessions that we will have next week. Okay, there we go. So join us again next week at 11 a.m. for Happy Math Hour. Math 1314 will be covering properties of logarithms, exponential, and logarithmic equations. And Math 1324 will be doing basic matrix operations and inverses. Our 1 p.m. session will be on health and fitness. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or your mic, and we hope to see everyone again next week for Happy Math Hour. Thank you.